Here are the quiz answers for reflection and refraction of light in this question. We know it's a concave mirror, and because it has a positive focal length, you have to find the height of the image. So first you have to find the image distance. And once you find the image distance, use the formula for magnification. You notice that the magnification is negative. It means that it's a real image, because you can see that the object is placed 100 centimeters and the focal length is only 20 centimeters. So it's placed outside the focal point. So it is a real image, and that's what the negative shows here. Again, magnification is HI by HO. So use that value of magnification to get the height of the image as -1 centimeter, which again shows that the image is inverted. Yes, because it's a real image. It's an inverted image. Here, just direct. Use n is equal to 1 by sine c to find the critical angle. (41.8 degrees). Again, same thing, you have to find the critical angle. In this case, again, the focal length is, actually we did this same question, number 1, so here is the answer, because we did this part, remember. We had already found out that the image distance was 25 centimeters, the same exact numbers. Again, it's a real image, and it's in front of the mirror. In this question, light ray is in water and it passes into air. Okay, so it's in water. So N1 is 1.33. Sine 40 is equal to N2 theta 2. And you got to find theta 2. Find sine theta 2 and find the inverse. You get 58.75 degrees. Here, John's face is 20 centimeters in front of a concave shaving mirror, and his image is twice as big and upright. Of course, it's a virtual image. That's why it's an upright image. You need to find out the focal length. Okay, so it's a virtual image because it's an upright image. That's very important. And for a virtual image, magnification is positive. Therefore, it's +2 is equal to -di by do, which gives you di in terms of do as -40 centimeters. Once you get that, use it in the equation. 1 by f is equal to 1 by do plus 1 by di to calculate the focal length. Now what's important is to remember that for a virtual image, magnification is positive, but for a real image, magnification is negative. All right, it's a special thing with magnification, because when you're talking about distances, if it's positive, it's a real. But only for magnification, real is negative. I hope you get that. Here you have a beam of light entering into a pane of glass, and the two different colors have slightly different refractive indices, and you're asked to find the separation as they come out. So first you can use Snell's law and find the angle of refraction for each one. So for the first one, you get 33.2 degrees. And the same way for the second one, you see that the refractive index is slightly different, so the angle is going to be very close. Okay, so find the difference between the angles, and then remember that this is the glass slab and the ray is just passing through. At this point, it breaks up into two because of the different refractive indices. One goes this way and maybe the other one goes slightly away from that, not the same path like that. And then they come out parallel, but you're asked to find this distance. So, and you know this angle already because we found the difference. We know this angle, you're asked to find this distance. And this is like the arc of a circle, which is equal to the radius times the angle. But angle has to be in radians. So first of all, x is equal to, the radius is 3 millimeters, which is actually the thickness, times 0.34 into radians. So that's why I multiplied by pi and divided by 180 in order to change degrees into radians. You get the answer as 0.017 millimeter. Well, what a question. You are 0.75 meters in front, and so your image will be 0.75 meters behind, so the distance is 1.5 meters between you and your image. You've got to read the question carefully. How far are you from your image? That's the question. Okay. And this one, the focal length is negative 25 centimeter, which means it's a convex mirror in this case. And DO is 100 centimeters. So just do the calculations carefully. You get negative 5 by 100 there. So when you take the reciprocal, or when you invert it, you get minus 100 by 5, which is minus 20 centimeters, which means the image is virtual. And of course, a convex mirror can only produce a virtual image. So that's right. Now, light enters this prism, and this equilateral prism. It's entering this way, and so the angle of incidence here is 90 degrees, right? And therefore, the angle of refraction must be the critical angle. Yeah, because everything in light is reversible. If it enters at critical angle, then it will refract at 90 degrees. Therefore, the reverse case is if it enters at 90 degrees, it should refract at critical angle. So this angle can be found out using the information given, which is the refractive index. So if you use that, you can find that angle. Let me call that theta C. Normally we call it theta 2 because remember this is theta 1, this is theta 2, but in this case it's theta C. Find that. And once you get theta C, you know that theta C plus theta 3 is the angle of the prism. Therefore you can find theta 3. It's an equilateral prism, so it's 60 degrees, of course. You get 18.9. From there, you can use Snell's law at that point and find out theta 4. And how much it bends is actually, I'm going to draw it after this, but it's given by theta 1 plus theta 4 minus A. Okay, now look at that diagram carefully. This incident ray was supposed to go straight if it did not bend, but finally it's coming out about this way. So the total angle between the incoming ray and the ray that leaves the prism is actually called the angle of deviation, and that's given by theta 1 plus theta 4 minus a from the simple geometry of this figure. So that's how you get that answer. The angle of incidence is given, the angle of refraction is given. It's quite a simple thing. Apply Snell's law and find the index of refraction, which is N2. Now, in this case, you have the optical fiber. The total length is 1 meter long, and it's entering by this phase. And then what's going to happen is, you don't have to worry about what happens when it enters, but remember that as it tries to go out into air, maybe here, it doesn't manage, and it's totally internally reflected. Same thing happens here, so it keeps going back and forth again. So that's where you're going to look at. So let me complete the diagram now. The ray enters, it's totally internally reflected, and again until it comes out the other end. So you can see a triangle there, and that angle is surely the critical angle, because it says what's the maximum number of reflections. So that means it just manages. Okay, so if you get that angle, because you know that it should be, the angle of incidence must be greater than the critical angle for it to remain inside the optic fiber. So first find the critical angle, which will be 50, that's too slow, okay, 50.28 degrees. Once you get that, in this triangle, if you look carefully, in this triangle, tan theta c is x divided by the diameter of the optic fiber, which is given. Okay, tan theta c is x divided by this. So, and that's 20 micrometer. That's why it's 20 times 10 to the minus 6. And so you get x as 24 times 10 to the minus 6 meter. Okay, so therefore the number of reflections required is 1 meter divided by that much, because in one reflection it's able to move that much forward, and we actually wanted to move 1 meter forward, right? So 1 divided by that would give you 41,533, which is approximately 42,000 reflections. And the last one, fish seeing the fisherman. The fish is underwater, and the ray of light from the fisherman reaches the eye of the fish. And from the diagram, you know that surely this angle is the critical angle, because the angle here is 90 degrees, right? I mean, here is 90 degrees. So this is the critical angle. And so you find the critical angle. And definitely that same will be the angle here, right? So the answer is about 49 degrees. Thank you and good luck.